In this video, I'll introduce a new term that goes along with distance, and this is the eccentricity of a vertex. So I'll introduce the eccentricity of a vertex. We'll look at an example of computing eccentricities of vertices in a graph, this graph. And finally, we'll also introduce some new terms, diameter, radius, central vertices, peripheral vertices, and antipodal vertices. So first off, what's the eccentricity of a graph? This is the distance, so the eccentricity of a vertex V in a connected graph. Again, we're going to assume our graph is connected. It's the maximum distance between V and any other vertex. So that is the eccentricity of a vertex V. It's the maximum of all the distances between V and any other vertex in the graph. So remember that distance was the minimum length of a path between V and W, say. So the eccentricity is a max of mins. So it's a maximum of a bunch of minimums. Right, this will be kind of, this theme will be important to keep in mind. So it's a maximum of all the distances between that vertex and every other vertex in the graph. So let's go ahead and compute some eccentricities here. So I'll start at V1. So I want to look at what's the distance between V1 and every other vertex in the graph. Okay, so the distance between V2 and V5 is 1. The distance between V1 and V6 is 2. Distance between V1 and V9 is 3, as well as V10 is 3. So the eccentricity is at least 3. Let's see. 1, 2, 3, 4. Right, the distance between U1 and U8, sorry, this should be V1. V1 and V8, 1, 2, 3, 4. It takes 4. The distance between V1 and V8 is 4. And this is the furthest vertex from U1, right? We could check all the other vertices, but hopefully you can kind of see that V8 is the furthest one. That is, the maximum of all the distances between U1 and any other vertex of the graph is 4. And so the eccentricity of V1 is 4. I'm going to go ahead and mark 4 here on the graph. And I'm going to look at V2 and V5. Or I guess I'll look at V2 first. Again, I want to do the same thing. I want to look at the distance between V2 and any other vertex in the graph. This time, let's see. I can find paths of, for example, distance between V2 and V10 is 2. It's 2 between V2 and V7, 1 between these, 1 between those. Here's 1, 1, 2, 3. It takes 3 edges to get from V2 to V8. So distance between V2 and V8 is 3. And in fact, for any vertex in the graph, any other vertex in the graph, the distance between V2 and that vertex is at most 3. That V8 is, again, the furthest vertex from V2, and so the eccentricity of V2 is 3. And so you really do just kind of have to check all the different vertices for each of these. Again, V5, 1, 2, 3. It does take 3, so the eccentricity is at least 3. And then you can check and see that, there's no distances there's no distance between V5 and any other vertex that's 4. If I just kind of run through all the vertices, I can get there at most 4 steps. Sorry, at most 3 steps. And so V8's the furthest one, so eccentricity of V5 is 3. And we just keep running through this. So from V6 to any other vertex, well, it takes 2 to get here, 1 to these, 2 to that one, 1 to that one, 1 to that one, 1 to that one, 2 to V8, 2 to V4. So the max of all those distances was 2. The eccentricity of V6 is 2. Back to V3, let's see, 1, 2 to that one, 2 to that one, 2 to that one, 1. It takes 3 to get to V9. So my eccentricity is at least 3. 1, 2. 1, 2, 1. So the eccentricity of V3 is 3. And we just keep running through this. So from V4 to 1 to all of those, 2 to that one, 3 to that one, 3 to that one, 3 to that one, 2 to that one, 3 to that one. So the max was 3 there, and we just keep doing it. So from V8, so we already know that from V8 to V1, that these are furthest from each other. This one's also 4. And we can check, I mean, we do have to check there's no other vertex that's further than U1, but we can check that, right? 1, 2, 3, 1, 2, 3. Yep, the furthest one is length 4. For V7, let's see. 1, 2, 3. Can I do better than 3 to get to V1? 1, 2, 3. 1, 2, 3. So distance from V7 to V1 is 3. I don't see any that are of distance 4 from V7. So that this is 3. Finally, we can check V9 and V10. We should verify that the eccentricity of each of these vertices is also 3. So I've put here the eccentricity of each vertex next to the vertex. Now you'll notice something, that any two adjacent vertices, their eccentricities differ by at most 1. So that is, if U and V are adjacent, then the absolute difference between their eccentricities is at most 1. You prove this with the triangle inequality. This is Theorem 2.7. And let's actually run through the proof of Theorem 2.7 here. So, right, in particular, because we get to use the triangle inequality. So, okay, so let U and V proof. Let U and V be adjacent vertices. In particular, the distance between U and V is 1. And we'll assume, without loss of generality, that the eccentricity of U is greater than or equal to the eccentricity of V. Right? If not, I'll just swap U and V. So let W be a vertex, such that the distance from U to W is equal to the eccentricity of U. That is, W is a vertex farthest from U. So that's what W is, vertex farthest from U. Then, right, so since we have D, distance between U and V is 1, and since the eccentricity of U is this distance, and the eccentricity of U is at least as big as the eccentricity of V, we can say that the distance from V to W, well, it can't exceed this eccentricity of U. Otherwise, it would have higher eccentricity. So this is less than or equal to the eccentricity of V. So now it follows that, so absolute difference between E of U, eccentricity of U, and eccentricity of V. Well, I know eccentricity of U is at least as big as eccentricity of V, so this is the same thing as eccentricity of U minus eccentricity of V. And so, right, eccentricity of U is distance between U and W. Really what's going on here is eccentricity of V is greater than or equal to the eccentricity of D, distance between V and W. And so, right, I want to bound here. So this will be less than or equal to distance, negative distance V to W. So minus distance from V to W. Right, I took the negative of these, so that flips the inequality. So I have a less than or equal to, right? Negative eccentricity of V is less than or equal to negative distance from V to W, right? Multiply both sides by negative, flips the inequality. So what is the, what do I do from here? what I want to say, right, so the triangle inequality says that the distance from U to W is less than or equal to the distance from U to V plus the distance from V to W. So there's the triangle inequality. If I rewrite this, distance from U to W minus distance from V to W is less than or equal to distance from U to V. So this, what I have here, is less than or equal to the distance from U to V, which is equal to 1. So eccentricity of U, difference between that and eccentricity of V, is at most 1. And so that's the proof of that theorem. So it just uses the triangle inequality, which is really handy with distances. Okay, so what else do I want to mention here? Well, I want to go back up to this graph for a second, right? I mean, you can notice, yeah, any two adjacent vertices, their eccentricities differ by at most 1. And that's, again, due to the triangle inequality. There's some other terms that go along with eccentricity, and that is diameter and radius. So the diameter, diam of G, of a connected graph is the maximum of all eccentricities. So that is diameter of G, so this is diameter of the entire graph, is the max of the eccentricities over all vertices in the graph. So remember that, right, this gets kind of wacky. So the eccentricity was a maximum of minimum lengths. Diameter is the maximum of all of those maximum minimum lengths over all vertices in the graph. So this is why this can get a little bit confusing. But if you just find the list, right, we have here the list of all the eccentricities, so it's not hard to pick out the diameter, right? In particular, if this is my graph G, the diameter of G is equal to 4. It's the maximum of all the eccentricities. So we can also see that the minimum of all the eccentricities is 2, and that's, so if diameter is the longest, so think of a circle, diameter goes from, right, from edge to edge through the middle. The radius, of a graph, G, denoted rad G, is the minimum of all eccentricities. So that is the radius of G is the minimum of all of the eccentricities over vertices in the graph. In particular, this one, for this graph over here, the smallest one was 2. That radius of G is equal to 2 for that graph. Okay, so going along with these two terms, diameter and radius, well, we want a name for the vertex that achieves a maximum, that actually achieves a vertex whose eccentricity is this diameter, and a vertex whose eccentricity is this radius. So, right, a vertex V with eccentricity of V equal to the radius of G. So this one, it's right, it's the vertex that's as close as possible to all the other vertices, right? It just takes 2 steps to get from V6 to any other vertex in the graph. So we call this the center, a central vertex of the graph. Is called central. So in my in our example here, V6 is central. 6 is a central vertex. And then what about for the diameter of vertex V with eccentricity of V equal to the diameter of G is called peripheral. So let's see. So V1 and V8 are peripheral. And finally, one more term to go along with this. So two vertices, U and V, such that the distance between them is equal to the diameter of the graph. So that is two vertices that are as far apart as you can possibly get in the entire graph, right? This is equal to the maximum of all the eccentricities, are called antipodal. They're on opposite sides of the graph. So an antipodal pair of vertices. So V1 and V8 are peripheral and an antipodal pair. So V1 and V8, right, each are peripheral, but the pair, V1, V8, that's an antipodal pair of vertices. All right, in the next video, we'll show some bounds on radius and diameter that will sort of further cement the nomenclature we're using here, right? We know that the radius of a circle is always half of the diameter. We won't get that exactly here with the graph, but we'll be able to say that rather that the diameter is at most twice the radius. So at most twice the radius. So not exactly, but at most. And we'll see that in the next video.